This tells you why I wanted more than anything else to have the job that I have today. I have my dream job. I feel incredibly fortunate. The University of California and Caltech co-own the largest telescope in the world. So why is this important? It's important because large telescopes come with two campaign promises. One is that you build a big telescope, and we describe how big a telescope is by the size of the mirror, the collecting mirror. And if you have a big collecting mirror, you can see things that are very faint. It's, because it's like a light bucket. You're collecting the photons that are raining in. So the bigger your light bucket, the more photons you can collect in a certain amount of time, which means that you can see things that are very faint. And in astronomy, faint means distance. So most astronomers really care historically about this aspect of being able to see the most distant universe, to be able to see the earliest moments in the universe, because light takes a finite amount of time to get from distant objects to us. It's like getting a history lesson. So it's a really important aspect of large telescope. What I care about is actually the second campaign promise, which is the larger your telescope, the bigger your diameter of the mirror, the smaller the detail that you can see. And the way I like to describe this aspect, your ability to get high angular resolution, is to make the analogy to the painting style of pointillism. So pointillism is made with a bunch of dots, and the closer you get to that painting, the better your ability to see or resolve the dots. If you stand further away, it all blurs together and it makes for a beautiful painting. So I want to see the dots. I want to see the dots that are as close to the center of the galaxy as possible. So I want to get my hands on as big a telescope as possible and to develop techniques that really take advantage of this aspect of telescopes. So this is why I love working at UCLA to work with this fabulous facility. Now you might ask, where is this facility? This is like asking, where is my lab? Well, you might say Los Angeles, but I'm going to tell you, actually, it's Hawaii. My lab is in Hawaii. Hawaii on the Big Island. So actually, the Big Island has been in the news quite a bit recently because of the volcano. So it's useful to remember Hawaii is a volcano. And I'll explain why the astronomers still think that Hawaii is the best place in the world to build big telescopes. So we're on the top of Mauna Kea on the Big Island. And the reason why Mauna Kea is such a fabulous place to build telescopes is that it's, for one reason, it's a very high peak. So we're up at 14,000 feet. So if you want to build a telescope, you want to get it on as high a peak as possible because you want to see through the atmosphere. And this is a picture that I actually took on the first time, my first trip up to the top back in 1994. And you can see the clouds below you. So that's useful because if you're like me and think of Hawaii, I usually think of a tropical place with lots of rain. That's not good for astronomers. And the reason why this makes sense is all of that is below you. Now, it's also true that 14,000 feet is a very challenging place to work in terms of human physiology. It turns out your brain doesn't function particularly well up at 14,000 feet, which is an interesting challenge. So you have astronomers, astrophysicists who desperately want to use this facility. The typical UC astronomer might get 2 nights a year. The operational cost of this telescope is evaluated at roughly $100,000 a night. So you do not want to be at suboptimal during your night of observing. And there are classic stories, like the astronomers who will write down the list of everything they should remember and then forget the list. Or in my case, the first time I went up with a graduate student, my first graduate student, we had an interesting debate up at the top, which was, what's 128 divided by 2? So these are one of the aspects that make doing astronomy challenging. So the way we do astronomy today has evolved quite a bit. We now no longer go to the summit. For many years in this experiment, we did go to the summit, which was an exciting adventure, and I loved going up there. But then it became possible to observe from the headquarters, which are in Waimea. There's about 100 people, 100 staff that are responsible for the operations of this facility down there, and it turns out you think much better at 1,000 feet. So that's wonderful. And now, since roughly the last 10 years, it's possible to control these facilities from campus. So now we work in concert with those people who are operating the telescope, but as the scientists, we can do this from campus. So every place comes with pros and cons. This is always the way it is with advancing technology. You get something, and you also lose something. So the things that we gain are better thinking, and certainly better educational opportunities by bringing the observations back to the campus. All right, now let's come to the volcano aspect of this. So the Big Island is composed of 5 volcanoes. One of them is active. That's Kilauea. That's the one in the news. And fortunately, it's a volcano. All the volcanic activity in Hawaii is for the most part pretty calm and not extremely explosive in the sense that you have seen in the news plumes, but you haven't seen anything that throws the dust up into the higher levels of the atmosphere, which would really be a problem for astronomers. But Mauna Kea Kilauea is a different kind of volcano. This is a picture of Kilauea from 1994 when it was in a similar state where you could actually see surface flows. So it is an interesting and exciting place, but we can carry out our observations during this. In fact, we had a night the other night where we could actually see an eruption that appeared on the front page of the Los Angeles Times the next morning. So it's exciting, but it does not disrupt. Mauna Kea is a dormant volcano, which means, according to the geologists, it's not going to do anything for another 1,000,000 years. Now, I have to trust them because I'm married to one, so we hope they got that right. Now, the other reason why the Big Island is such a great place, and in particular Mauna Kea, to build telescopes is that you want not only a high site that gets you through most of the atmosphere, but the atmosphere that you have left, you want the airflow to be very smooth, what the scientists call laminar. And to get very smooth airflows, you want to be around a large body of water. So to be on an island actually optimizes this. So if you look at the forefront facilities that are built today around the world, you'll notice they're on high peaks near big bodies of water. So the Andes in Chile, the Canary Islands, and the Hawaiian Islands. And that's the reason you're getting this very smooth airflow for going to a high peak near a big body of water. Now, the next thing you want for a large telescope is a dark site. You work very hard to collect these precious photons from across the universe or across our galaxy. And they've been traveling to us for a very long time. In the case of the galactic center, the center of our own galaxy, those light packets, those photons, have been traveling to us for 26,000 years. So the last thing you want to do is have them messed up in any way or contaminated. So a dark site where you don't have local light is incredibly important. So this introduces a very interesting tension in the world of astrophysics, because you want to be both in a very dark place and you're trying to build incredibly advanced technological buildings and facilities and instruments. So you want access to high-tech industry. That tends not to be in dark places. So you're trying to optimize this trade. So Hawaii is one of the few places in the world that provides you with relatively good access to high tech, both in terms of the industry and the people. It gets satisfied nicely in Hawaii. So you want it high tech and you want it dark. So that's the piece about the darkness. Okay, so now we have a telescope. We have it in Hawaii. We've explained why we want it in Hawaii. Let's come back to the problem or the promise of getting very high resolution information, the second campaign promise. So the problem is, while it's high, you're still looking through quite a bit of atmosphere. And it's smooth, but still not that smooth. And you can see that by looking at this picture. These are data that we took when this experiment started back in 1995. It was the original data type. And the trick there was just to take lots of short exposures and you freeze the interfering effects of the Earth's atmosphere. And if there were no atmosphere, each of the 5 stars that we're looking at here prominently would be the size of the smallest structures that you're seeing and rock solid. That's not what you're seeing. You're not seeing this because these photons that have been coming to us for 26,000 years hits the top of the atmosphere 30 microseconds before it hits your telescope. So they say accidents happen close to home, and that's true in the case of these photons. Okay, so I'm super interested in how do you overcome this problem? How do you beat the atmosphere? Oh, and I should also say another analogy for how to think about the problem with the Earth's atmosphere is think of a river moving by you, and you're trying to look at a pebble on at the bottom of the river. And if it's moving and turbulent, it's very difficult to get a picture of the pebble. That's what's happening here. I'm trying to see through a stream of atmosphere that's turbulent. So the analogy works fairly well. The other analogy that I like to make in terms of what's happening and what we're trying to accomplish is to think of a circus funhouse mirror, and it distorts you. So that's what's happening to the starlight. It's getting distorted. And I want to figure out a way of putting a second mirror in there or some process that makes me look flat again. Okay, so astronomers have looked and thought about this for a long time. So if you want to beat the atmosphere, one very straightforward and effective way of doing this is you get above the atmosphere. And that is the solution of the Hubble Space Telescope. It is a incredibly powerful telescope that is not affected by the Earth's atmosphere. So we use this for our work, but the reason why for the work that I'm going to just share with you today, that I'm sharing with you today, that Keck is the choice instrument is because it's bigger. So the diameter of the Hubble Space Telescope is 2.4 meters. The diameter of Keck is 10 meters. You want to kind of visualize that. That's like the width of a tennis court. And the power of the diameter for the kind of work that I do goes as the diameter to the 4th power. So I've got a telescope that's 4 times bigger. So that's 4 times 4 times 4 times 4. And because I'm not at the summit of Mauna Kea, I actually can do that math. And that's a factor of 100 better in principle, if I can figure out how to make that, to take the blurring effects out. So as you might imagine, if you're being offered the opportunity to do something 100 times better, you're probably going to work pretty hard at it. So that's what I've spent a large part of my career thinking about, which is what techniques can we use and develop to beat the atmosphere. One of my advisors said when I was a grad student, you know, Andrea, you just take the twinkle out of stars. That's my job. So this is an animation that shows some of the work that we've done. It captures what happens if you take a very long exposure in time on the center of the galaxy. So you can see the 5 bright stars that we were seeing the bug splat patterns for a moment ago. And those were short exposures. Those were 1/10 of a second. And they're at 2 microns. That's the wavelength that we do our primary work at. And if we use these techniques, we can get to the highest resolution afforded by the telescope, which is the resolution is about a factor of 20 times better. Okay. Now, the technology that we've been using and developing has changed radically over the last 20 years. So this project is very much technology-driven discovery. So at each phase, where we are in our technological development has sort of dictated how much science we can do. And I have to share, this has been an incredibly exciting journey. When I first started this project 25-ish years ago, I wrote my first proposal. I was a brand new assistant professor. I thought I had such a good idea for how to use this telescope in a new and different way. And you have to apply for telescope time. And this committee, this group of people said, well, this idea that you have for how to collect the data probably won't work. And even if you do, you probably won't see stars at the center of the galaxy. And even if you do, that are close enough, and even if you do, you won't see them move. Okay, so that's a lot of no's to get at the beginning. But fortunately, I'm used to being told you can't do something as a woman in physics. So I said, okay, fine. I've heard that before. Let's keep going. And I also work in a department that is, I'd say, very supportive. So these are colleagues, and I think this is a comment on how science works. You can't do it in isolation. You actually need the support of others to be successful. I think there was a comment in the gala about that that just so resonated with me. So I had a colleague who lent me his telescope time, which is, you can't give it back. So enabled us to show that this technique would work. And this is just a picture showing the original instrument. So it was an instrument that was designed for the facility, and we just built, this is in collaboration with my colleagues, a little adaptation that allowed the instrument to see on a smaller scale than it was designed to do. And I think this is also an interesting comment. This is a $100, $200 million scale facility that they're letting an assistant professor come and add a little tweak to it. That is also a rather amazing comment about this particular facility in terms of its willingness to engage in doing something different or outside the box. Okay, so this was what we did for the first 20 years. It was hardware simple, which means not very expensive, computationally complex. So you basically take a little bit of data back and you spend a lot of time developing software and algorithms to figure out what did the atmosphere do versus what's the true underlying object. And there are a lot of people out there who care about that. It's not just the astronomers who think a lot about seeing through the atmosphere, both up and down, and working out the image. That's the military, if you hadn't figured that one out. There is also the whole medical industry that's interested in imaging through tissues, either through your eye or various parts of your body, and want to figure out what you're trying to see underlying some distorting media. So from a technique perspective, there's a lot of reasons to think about this outside of astronomy. It's not why we do it, but we want to see the universe. Okay. The way this story evolves now is that there's a hardware solution to this, and this is a solution that was developed by the military. And as the astrophysics community was making progress in figuring out much more sophisticated hardware solutions, the military basically said, oh, and I should say, the funding for astronomy and astrophysics is nothing compared to the funding in the military. So as we were starting to ask for funding to do this, the military said, basically, we know how to do this, and declassified it. So in the mid to late 90s, there was this huge thrust forward because of a declassification. And this was really exciting, and I was really excited because I knew this would be completely revolutionize what we were doing at the center of the galaxy. Now, this animation shows both a couple of miracles, like the dome going away, but it also is designed to help us talk about how does adaptive optics, which is this new technology, work. So we see a beam of light coming into the telescope. The mirror was the thing it bounced off of, and then it goes into an instrument bay. And the instrument bay is where all the magic happens for correcting or taking the blurring effects out. So we're going to see both the beam of light, and in a minute, it's also going to be shown in a second way you can talk about light, which is a wavefront. And if there were no atmosphere, each wavefront would be a flattened pancake. So you can see in this the beam going through, bouncing off various mirrors. And if you don't do anything, it's that bug splat pattern again. And it's going to show you in a very important element. This is called the deformable mirror. This is the second Circus Funhouse mirror that takes out the distorting effects. So rather than pancakes coming in, we have Pringles potato chips. And then you have this second mirror that when it's not on, it doesn't do anything. But if it starts to look at what the past wavefronts look like, then it bounces off into these flat pancakes. So if the system works, fully understands or can fully probe the atmosphere, it is a perfect image at the end of the day. So it gets nice and tight. And for the first time in our work at the center of the galaxy, we can take an exposure that's longer than 1/10 of a second. So the kind of work that we can do is so much more powerful with this technology. Okay, and now you might ask, how do you know how to move that deformable mirror? And a key aspect of that is that we shine lasers into the atmosphere. And we do this because up at about 90 kilometers, there's a very thin layer of sodium atoms, just a fluke of nature. So I love shooting stars, or making a wish on shooting stars, because those are not really stars. Those are meteorites or meteors coming through the atmosphere and burning up. And the sodium atoms in those meteorites or meteors get trapped at 90 kilometers in this very thin layer that's about 4 kilometers thick. So you can take a laser that's tuned to a transition in the sodium atom and stimulate those atoms to shine. So that's an artificial star. And we can then look at that artificial star. We can create it in any direction we want, and use the light from that artificial star to inform us about how to change the deformable mirror. For me, this was an amazing night. We actually got telescope time on both telescopes. So you only need one laser per telescope, but it's like 2 laser pointers showing you the roadmap to the center of the galaxy. If you want to look up at the center of the galaxy, it's up this time of year. You find the constellation of Sagittarius, which is the teapot, and it pours into the center of the galaxy.